Hey guys, welcome to Analytics Vidya. In this video, I'm going to give you a very brief history of large language models. During the next 10 minutes or so, I'll give you a comprehensive walkthrough of the events that were key milestones to the ultimate development of large language models, or LLMs as we call them. If you're new to the channel, do hit the subscribe button to get free access to our awesome generative AI material and projects. On this note, let's begin. Way back in 1966, the world witnessed the birth of Eliza, which is considered to be the first ever chatbot built by humans. Created by Joseph Weizenbaum at MIT, Eliza was a groundbreaking experiment of its time, enabling human-computer interaction. It didn't understand the conversational context in a way we humans do, or for that matter, ChatGPT does nowadays. Instead, it merely created an illusion of a conversation by rephrasing its user statements as questions back to them. Smart, right? For example, if a user typed, "I'm feeling sad," Eliza would respond by saying, "Why do you feel sad?" At that time, many variations of the chatbot were made, and one of the most well-known variation was called Doctor. You can actually try this out on this webpage. While Eliza was a humble beginning, this surely paved the way for further research in the field of chatbots and natural language processing in the years to come. As a fun fact, just recently in 2018, Eliza went viral again when it got featured in an episode of TV show Young Sheldon. Moving on into the late 20th century, we saw emergence of neural networks which were deeply inspired by human brain and its interconnected neurons. Among these, recurrent neural network, or RNNs as we call them, were the first to come in 1986, and they gained instant popularity. Unlike traditional feed-forward neural networks, where the flow of information was in one direction, RNNs could remember previous inputs in their internal state or memory thanks to their feedback loop, making them suitable for natural language processing tasks. Now, what do I mean by this? Let's understand this with this simple sentence: Tom is playing cricket in the garden. Once you read this sentence, I'm sure you can answer questions like who is playing, what is he playing, where exactly is he playing. But how do we do that? We do that thanks to our human brain that memorizes the keywords Tom, cricket, and park from the sentence, along with their relationships. Now, RNNs also had this ability to store key information in its memory. So just like humans, RNNs could also answer these bunch of questions based on the context. But hey, while RNNs were a significant step forward, they had limitations, especially with long sentences. In simple words, they suffered from long-term memory loss, just like these guys. To understand this, let's consider this longer version of our example sentence. Tom is playing cricket in the garden along with two of his friends. By the way, guys, in reality, these sentences tend to be even longer, having hundreds of tokens. For this particular sentence, if RNNs were to answer who is his in this sentence, they would fail. And this happens because they were not good at retaining memory for long enough. In technical words, RNNs had this problem of vanishing gradient, and it needed to be fixed. Long short-term memory, or LSTM, came up in 1997. LSTMs were a specialized kind of recurrent neural networks. Their primary advantage was their ability to remember information over long sequences, overcoming the short-term memory limitation of RNNs. Now, how did they do that? Well, LSTMs in their unique architecture introduced the concept of gates, especially the input gate, forget gate, and output gate. These gates determine how much information should be memorized, discarded, or output at each step of the way. This selective ability to memorize or forget helped LSTMs maintain relevant information in their memory at all times, making them more efficient at capturing long-term dependencies from sentences. So if we consider this example sentence again, LSTM is able to retain context better and is able to resolve the co-reference resolution of the word his to its subject Tom. Awesome, right? In 2014 came gated recurrent units, or GRUs. They were designed to solve some of the same problems as LSTMs, but with a simple and more streamlined structure. Just like LSTMs, GRUs were designed to combat the vanishing gradient problem, allowing them to retain long-term dependencies from sentences. GRUs simplified the gating by using only two gates rather than three, which was the case in LSTM. They had update gate, which determined how much of the previous information to keep versus how much of the new information to consider, and the reset gate, which determined how much of the previous information to forget. The reduced gating in GRUs made them more efficient in terms of computation. As it turns out, RNNs as well as RNN-based LSTM and GRU architectures weren't great at retaining the context when it was far away. The NLP world and their problems needed something more, and that gave birth to the concept of attention, which was published in this 2014 paper. The introduction of the attention mechanism marked a significant paradigm shift in sequence modeling, offering a fresh perspective compared to previous architectures. Let's go deeper into this. Well, RNNs would process sentences with a fixed size context vector. What this means is that they tried to cram all the information of a source sentence, regardless of its length, into a single fixed length vector. And because of this, their performance deteriorates as the sentence length increases. This figure shows how the performance of RNN goes down as we increase the length of the input sentence. In contrast, attention allows the model to look back at the entire sequence dynamically, selecting different parts based on their relevance at each step of the output. This ensures that no crucial information is lost or diluted, especially in case of longer sequences. Let's look at this short example sentence to understand attention better. The sentence is, I fed my cat because it was hungry. Now let's say we want to translate it into Hindi or let's say French. A typical RNN model would first read and process the entire sequence, remembering keywords, let's say I, fed, cat and hungry in its internal state or memory. Post that, once it starts translating, it might probably face issue with the word it because it forgets whether it refers to the subject I or cat and leads to incorrect translation. Whereas attention model, when translating the word it, has the capability to look back at the entire English sentence, highlighting, let's say, cat and hungry as relevant, and thus helping the model accurately translate it as referring to the cat. Now, can you guess what happened next to this? Well, if we were to pinpoint a moment when the AI community collectively gasped in awe, it would be the introduction of transformer architecture that came out in the year 2017 with the release of this paper famously called Attention is All You Need. Ditching recurrence entirely, transformers relied on attention mechanism to process sequences. At its core, it's composed of an encoder and a decoder, each with multiple stacked layers of self-attention and feed-forward neural networks. A standout feature is the multi-head attention, which allows it to focus on different parts of the input sentence simultaneously, capturing various contextual nuances all at once. Another highlight was its ability to process sequences in parallel rather than sequentially. It was this very architecture that laid the foundation for subsequent models like Google's BERT, OpenAI's GPT, and more, driving us into a new era of large-scale language models. With the success of transformers, the next logical step was scaling. And this kickstarted with Google's BERT model, which was released in the year 2018. Unlike previous models that processed text either left to right or right to left, BERT was designed to consider both directions simultaneously, hence the name bidirectional encoder representations from transformers or BERT. Pre-trained on vast amounts of text, BERT was the first proper foundational model that could be fine-tuned for specific tasks, setting new performance standards across various NLP benchmarks. Post that, literally the floodgates opened up with OpenAI releasing its GPT-2 model and Google releasing its T5 model in 2019. Thereafter, GPT-3 came up in 2020. And then between 2021 and August 2023, which is the present time, these LLMs could perform innumerable tasks, making a paradigm shift in AI capability. From the rudimentary rule-based systems of the 60s to the colossal LLMs of today, the journey of language models has been nothing short of spectacular. If there's any important milestone you think we have missed, do let us know in the comment section below. Could it be word embeddings? What do you think? Anyway, thanks for watching. I'll see you in the next video. Bye.